Hi everyone, so this is a review for Chapter 2 revision quiz. So based on the responses received below, I think it's appropriate for us to just discuss all the questions maybe, because almost all of them got more than 25%. Okay, so let's move on. Question 1. Question 1. A parallel plate capacitor is charged in air. It is then electrically isolated and lowered into a liquid dielectric. Which of the following sets of changes is correct? Okay. So what does it mean here is if we have a parallel plate capacitor which is now charged in air. When they say it's charged in air means by they are probably connecting it to a power source. That's the first thing, charge. The second thing that they say in air means by the plates are filled with air in between. Okay, so that's the idea of charge in air. Then they say it is then electrically isolated. Electrically isolated means by you don't provide a loop for the charge to move. Okay, in that case, you can say it is charge isolated or electrically isolated. Means that the charge is unable to move from one place to another. In this case, from one plate to another plate is impossible because you isolate the charge by breaking the circuit. You don't allow the circuit to be there. Okay, then it is lowered into a liquid dielectric. So when you lower it into a dielectric, I assume it's now immersed in some kind of liquid. So because there's this liquid dielectrics in between the plates, you can say that there's dielectrics in between the plate now. So what is the effect of liquid dielectric? It's the same as any solid dielectric slabs that you have learned before. The first effect is probably that it will increase the capacitance. So the capacitance will increase. Why? Because usually dielectrics come with a relative permittivity. So because of this relative permittivity being more than 1, and it also represents the ratio of the C with dielectric divided by the capacitance without dielectric. And since we know it's greater than 1, so we will know that C over C0 is definitely greater than 1. So we know C will definitely be greater than C0. So the capacitance with dielectrics, the capacitor with dielectrics will have a greater capacitance compared to a capacitor filled with air or a capacitor in vacuum. So that's the effect that we know. So now if we proceed further and study how will the other variables change. Let's say we know C is equal to Q over V, right? So how does Q change? How does V change? This one we have to be very sensitive to the setup here. If you look at the setup here, this capacitor here is not connected to any circuit. It is not connected to any circuit, charge cannot flow. So if charge cannot flow, the Q here has no possibility of increasing or decreasing. Once the charge just can't come in, the charge just can't get out. It's stuck here. So the Q should be constant. So if the Q is constant and the capacitance is increasing, we can therefore arrive at the conclusion that V should be increasing. So not increasing, sorry, decreasing. Okay, so the potential difference across the plate will actually decrease due to the dielectric. In that case, you can say that the capacitance is increasing. This part is correct, this part is correct, this part is incorrect, and the charge should be constant. So when they say charge increase, that's wrong. The potential difference decrease, that's correct. So our answer will be this one. The capacitance increases and the potential difference across the plates decreases. So this is question 1. Question 2. The electric field between the plates of an air space parallel plate capacitor is E. Okay, so again you have a parallel plate capacitor. Then this parallel plate capacitor here, it's airspace. Okay, so inside here there will be, of course, because of it being oppositely charged, then you have a uniform electric field in between the two parallel plates. Okay, so this is how you actually produce a uniform electric field. Okay, so this is the electric field E. So now without disconnecting the charging voltage. So it's very important to remember that the battery is probably still here. Okay, the battery is still there. So an insulator of relative permittivity of 2 is inserted in between the plates. So I believe you have some kind of a dielectric here that is now being inserted into the in between the two plates. So it's being brought in here. So what would they ask for the final electric field between the plates. Okay, so what happens when you insert a dielectric in between the plates is initially you have two plates. Okay, let's draw back the situation here. If you have two plates and you have charged both sides of the plate with opposite charges, say because now this is plus Q and this is negative Q, and because of that you will have a potential difference across the the two plates. Okay, you have a potential difference across the two plates because you charge both plates with oppositely charge both plates with opposite charge. Okay, and the charge store on both plates should be the same, just that oppositely charged. So with that you create a V, and the result of a potential difference on while having potential difference, you also create a uniform electric field in between. Okay, now if you add on a dielectric inside the in between the two plates right now, introduce a dielectric here. So what will happen is the particles, the molecules inside the dielectric will reorient themselves. Reorient means like they rotate a bit themselves in a way that they will induce some kind of induced charges on the surface of the dielectric slab. Okay, so this is the dielectric. The pink color box here represents the dielectric, and this is the surface of the dielectric. So because of this polarization effect, we call it polarization effect, we induce an oppositely charged induced surface charges on the surface of the dielectric. So this plate is positively charged, right? So you induce negatively charged uh, on the surface of the dielectric. So that's for the positive plate. For negative plate, you probably have also induced charges but opposite sign to negative Q, so a positive charge. Okay, so because of these induced charges, what happens is you create an electric field also, but this electric field is in the opposite direction now. Okay, it's in the opposite direction. So because this thing is because the electric field now, you have components to downwards, you have component upwards. So what happens is they are supposed to cancel each other out. Maybe something like this. They are supposed to cancel each other out, so something like this. Okay, this is just a rough representation, a very graphical representation. The true thing is a bit complicated compared to that. Okay, so this is what happened. So your uniform electric field, the magnitude of the uniform electric field actually decreases, and in that case the potential difference is supposed to decrease, okay, while keeping the Q constant. But your situation now is very unique. The situation now, they continue to connect this capacitor to a battery. And this capacitor here is connected to the battery. So in this case, it's a different story already, because your battery here will supply a very constant voltage to the charges that pass through it. So let's say if this battery here supplies 5 volts, it means by each coulomb of charge that pass through it gets 5 joules. So the 5 joule has to be charged over here. Okay, so what does it mean here is your V over here must be equal to 5 volts as well. No matter you bring in what kind of dielectrics, you have to keep the potential difference across the plates constant, because that's how much energy being supplied to the capacitor. Okay, so in that case, if you are forced to keep the potential difference constant, now your electric field is reduced already. So how are you going to fix the situation is you are forced to bring in charges, bring more charges that was previously at the negative plate. Let's say here there's still some negative charge, right? And positive charge, right? It's a mix, so it's negative plate, so there's probably more negative. So the positive plate here, probably it's more positive. Just a rough idea, a rough representation. So that's why, because there's more plus up here, then that's why it's positively charged. There's more negative charge here, that's why it's negatively charged. So in order to keep the potential difference constant, what can you do is essentially you can bring more charges from the negative plate and shift it to the positive plate. In that case, you might need to remove some of the negatively in some of the positive charge over here. Okay, let's say I take out these two. So what I do is I bring those positive charge upwards. Okay, so because I bring those positive charge upwards, essentially I can recreate the electric field downwards. And so that's how I recreate the electric field to make it constant, initial and final, the same magnitude of uniform electric field. Okay, so the main message, if you can't understand the part just now, the main message is the V is constant because you are connecting it to the battery. Okay, so let's move on. If our V is constant based on this thing, if we insert a dielectric, the capacitor will definitely have a greater capacitance, but the potential difference across the plate must be constant if you are connecting it to a power source. Okay, so in that case, if the C is increasing, Q should be increasing. But that's not what we're trying to aim for. What we're trying to aim for is electric field. We know electric field will be related to potential difference across the plate. So to understand this relation, you have to go back to chapter 1 for parallel plates. For two parallel plates producing a uniform electric field, the electric field created will be equal to the potential difference between the plate and the separation distance between the plate. So these two parameters here actually control the magnitude of the electric field being created in between the parallel plates. So once we know that, we can change it into the form that we usually use in chapter 2. Why we need to change? Because in chapter 1, right, potential difference is represented by delta V. Once you move on to chapter 2 and onwards, the potential difference is eventually reduced to become V. Okay, so that's the equation if you are going to use it in chapter 2. So we know that V is constant. From up there, we know that V is constant. And there's no such mention that your separation will be increasing or decreasing. There's no such thing. So if your V and D are both constant, in conclusion, you can find out that the electric field will be constant. So in that case, we can arrive at the answer E, because we know that the electric field, the uniform electric field, won't increase or decrease in magnitude. Question 3. Both the parallel plate capacitors shown in figure A and B have the same dimensions. So this capacitor here and this capacitor here have the same area and have the same distance apart. Same for this capacitor and this capacitor, they have the same area and they are having the same distance apart. Which of the following pairs of comparison between V1 and V2, Q1 and Q2 is correct? Okay, so based on the situation here, we need let's do it one by one. Okay, let's look at figure A first. Okay, figure A, there's two capacitors which is being connected in series. Okay, so if they are being connected in series, I think you learn from class that if in series, then Q1 will be equal to Q2. Okay, Q1 equals to Q2, that will mean by C1B1 is equals to C2B2. And if you reshuffle a bit, then there will be C1 over C2 is equals to V2 over V1. Okay, the next thing that we know about this situation here is C1 will definitely be greater than C2. Okay, because these two are capacitors with the same dimension. So if you insert a dielectric into capacitor 1, for sure the capacitance of capacitor 1 will increase. Before that, they are the same. Now one of them is increased, so we know that capacitor 1 will definitely have greater capacitance compared to capacitance 2. Okay, since we know that now, we can arrive at a conclusion that C1 over C2 will be greater than 1. If C1 over C2 is greater than 1, because C1 and C2 is equal to V2 over V1, we can know that V2 over V1 will be greater than 1. And that will mean by V2 is greater than V1. Okay, so the next thing that we'll look at is figure B. Figure B are two capacitors being connected in parallel. So when it comes to parallel, you'll know that V1 will be equals to V2. Why are they equal? Because they are connected through the same wire. So the wire should not have any potential difference. The potential all along the wire should be the same. Okay, if here is 5 volt, then here should be 5 volt, then here should be 5 volt, here should be 5 volt. If here is 0 volt, then here should be 0 volt, then here should be 0 volt, here should be 0 volt. So if this is 5, this is 0, then this is potential difference of 5. And of course, this one will be potential difference of 5 as well. Okay, so that's why V1 is always equal to V2 if you're connecting the two capacitors in parallel. Okay, so we know that V1 is equal to V2. What kind of things can we say? We know that it will be equal to Q1 over C1. It will be equal to Q2 over C2. So what can we say right now is let's again shuffle things around a bit. So we know that C2 over C1 will be equal to Q2 over Q1. So if I tell you today that C1 is greater than C2, C1 is greater than C2. Okay, again similar situation, C1 is being inserted with dielectric, so C1 will be greater than C2. So from there, we are able to know that C2 over C1 will be smaller than 1. If C2 over C1 is smaller than 1, then Q2 over Q1 will be smaller than 1. And that will mean by Q1 is greater than Q2. Okay, so with all the things that we have said just now, we are able to arrive at the conclusion that the answer should be this one. V1 is smaller than V2, whereas Q1 is greater than Q2. Question 4. A charged capacitor X is connected in parallel to an identical but uncharged capacitor Y. Which of the following statements about the capacitors is true? Okay, so you have two identical capacitors. One of them we call it capacitor X, one of them we call it capacitor Y. So capacitor X is charged, capacitor Y is uncharged. So now if you connect these two capacitors in parallel, just like what I did here, if you connect the switch over here, what would happen to this capacitor over here? Okay, so let's write out the old situation here, the original situation, the initial situation. Initial situation, what happened is you have capacitor X, which has Qx over Vx. Okay, whereas for capacitor Y, you will also have Qy over Vy. Okay, so what we know for now is that capacitor X is charged, capacitor Y is uncharged. So capacitor Y should not have any charge stored in it, so Qy should be 0. And because Qy is 0, therefore Vy is also 0. There's no charge stored, then there should not be any potential difference across them. So now, what if we connect the circuits right now, like what I have drawn just now? When we connect a circuit, you have Cx prime equals to Qx over Vx, whereas Cy prime will be equals to Qy over Vy. Oops, I should label everything with prime because all of these are new situation over here. So Cx and Cy, both of them should be the same as the initial condition. Both of them should be constant, should be the same as the previous situation, because you are not changing the dimension of the capacitor, you're not changing the area, you're not changing the distance of separation, you're not adding dielectrics or changing dielectrics for the capacitor. So the capacitance should be kept constant. But right now, when you connect the circuits like what I've shown over here, what will happen is there's plenty of charge here, but there's lack of positive charge over here. And so here should be higher in potential compared to here. Okay, so what will happen is there will be positive charge that moves from this capacitor X to capacitor Y. So what we might observe is something like this. You might see charges move from the upper capacitor to the lower capacitor, something like this. Okay, so I believe the opposite side should have similar situation where you see something like this. Okay, the charge will keep moving from the capacitor X to capacitor Y until a stage where the potential across this plate, this positive plate, and this positive plate are the same. There's no potential difference between them. When there's no potential difference, only charge will stop flowing. Okay, you need potential difference for charge to flow. So the charge will keep on flowing from capacitor X to capacitor Y until the moment where the plates of capacitor X and the plates for capacitor Y share the same potential. Okay, just a rough example, putting numbers in. If previously here it was 8 volts, previously here it was 8 volts, and here it will be 0 volts. Then what happens is when you connect the circuit here, the potential here will be decreasing. It will be decreasing until a point where both capacitors share the same potential for one plate. Okay, so this one is for this side. Then probably for the other side, let's say it starts at 0. Let's just don't talk about the other side. Okay, the idea is that this potential and this potential should be the same. The negative plate also the same idea. This potential should be equal to this potential. So if this potential is equal to this potential is equal to this potential, the potential difference across capacitor X will be equal to the potential difference across Y. Okay, so Vx prime and Vy prime should be the same. Okay, so what else do we know about situation before we move on to other situation? Because Vx prime is equal to Vy prime, let's just call it equal to V prime. It's easier. Then the next thing that we know that is Qx prime plus Qy prime is equal to Q prime. Qx prime plus Qy prime is equal to Q prime. The idea behind this thing is there's no big idea actually. It's just conservation of charges. So if let's say you have 8 coulomb of charges stored over here, let's say there's 3 coulomb of charges moved from capacitor X to capacitor Y. So of course, capacitor X will lose 3 coulomb of charges to become 5 coulomb. Will lose 3 coulomb of charges, then capacitor Y will gain 3 coulomb of charges. Just that you cannot destroy or create any charges out of nowhere. So if here you lose 3 coulomb, then here you gain 3 coulomb. It's just conservation of charges. And since Q prime, we already label Qx prime and Qy prime to become Q prime. You can say that Q prime is equals to Qx. Why Q prime is equal to Qx? Because before that, all of the charges are stored at capacitor X. Then after that, that amount of charges that is stored in stored in capacitor X initially is being distributed to the new distribution, which is a portion at capacitor X, a portion at capacitor Y. So if you add up the portion received at capacitor Y with the portion of charge stored at capacitor X, you add them up, it will be the initial charge stored at capacitor X. Okay, so that's why we can say Q prime is equal to Qx, because Qx prime plus Qy prime is equal to Q prime. Okay, so with all this information here, I believe we can start to eliminate some of the choices here. So let's see, the potential difference across the capacitor X remain unchanged. Is that true? I don't think so, because just now as we explained, the potential difference across capacitor X actually decreased, the potential difference across Y actually increased. So let me just jot it down first. This one will be decreasing, this one will be increasing. So with that said, we know that the potential difference across capacitor X will not remain unchanged. It will actually decrease. Okay, so A will be false. The second option, the total charge and the energy are conserved. We know that the total charge is conserved, but we are not sure about the energy. So if later there's a necessity to talk about energy, then we'll talk about it. Okay. For this next option here, the charge in X decreases. Yes, we have already labeled that it decreases. Qx actually decreases, but its potential difference remain unchanged. Are we sure? Potential difference across X should decrease actually, because we say Vx actually decreases. So the potential difference does not remain unchanged. It actually decreases. Okay, so we have removed two options from our four selections. The last selection, the total charge is conserved. This one is true, but the potential difference across X decreases. Well, we also know that Vx actually indeed decreases. Yes, so for here, I think we have already got our answer. Our answer will be D. The total charge is conserved, but the potential difference across X decreases. Okay, we put a question mark here to talk about energy, right? So let's attempt to talk about energy probably. Okay, let's again write about initial and final energy. Some leftover. Okay, the initial situation here, we should call it U. Initially, there's only one capacitor being charged. So we can say that this will be half Qx Vx. Okay, half Qv is the formula for energy stored in a capacitor. For the final case, which we call it U prime, you have energy stored in both capacitor X and capacitor Y. So it's very careful, you need to be very careful and label everything clearly. You have Qx prime, you have Vx prime, plus you have Qy prime and Vy prime. Okay, we know from earlier that Vx prime is equal to Vy prime is equal to V prime. So what can we do is we can factorize out the half and the V prime and left it with Qx plus Qy prime. Okay, both of them should be prime. Once we reach this state, we see that in our equation mentioned here, we see that this Qx prime plus Qy prime is equal to Q prime. So actually we can still modify our equation to become Q prime V prime. But again, from the second equation over here, we see that Q prime is actually equals to the initial charge stored at capacitor X. So we can further change this to become half Qx V prime. Okay, so if you now put this initial and final energy in comparison side by side, you see that the only difference between them is the potential difference. For the first, the initial situation is Vx, for the final situation is V prime. So I believe if you want to see whether the energy is conserved, increases or decreases, you have to find out what's the relationship between Vx and V prime. If V prime is greater than Vx, then the energy increases. If that Vx is greater than V prime, then the energy decreases. If Vx is equal to V prime, then the energy remains constant. So how are we going to determine this? Actually, to determine the relationship between Vx and V prime, what can we do is we can write Qx prime plus Qy prime equals to Q. Okay, why we start from this equation is this equation here is an equation that includes the new situation and the old situation. Why do I say it includes the new situation and the old situation? Because Qx prime and Qy prime over here, they are both belonging to the new situation where the charge has been redistributed. But this Q prime over here, actually we can relate it back to the old situation, which is the initial charge stored at capacitor X. Okay, so this Q prime here can actually be changed to Qx. So now we can actually try to manipulate this equation by converting charge to be expressed in terms of capacitance and potential difference. So now here will be Cx Vx prime plus Cy Vy prime. Then this one will be Cx dx. This one should not have a prime because this is the old situation over here. Okay, so what can we do now is we know that Vx and Vx prime and Vy prime belong to the same value, so you can bring them out using V prime. So V prime will be V prime times Cx plus Cy equals to Cx dx. Okay, so what you can do now is you can rearrange the equation to be something like this. For V, Vx divided by V prime is Cx plus Cy divided by Cx. Okay, so here it's where it's going to start to be interesting. Okay, we know that Cx plus Cy divided by Cx is equivalent to 1 plus Cy divided by Cx. So we know Cy is a positive number, Cx is also a positive number, so Cy over Cx must be a positive number. So what can we know here is actually Cx plus Cy divided by Cx is greater than 1. Okay, so if Cx plus Cy divided by Cx is greater than 1, then Vx divided by V prime will be greater than 1 as well. So in that case, we can say that Vx is greater than V prime. So if we say just now, look back at this equation, if Vx is greater than V prime, Vx is greater than V prime, then the initial energy will be greater than the final energy. So in that case, we can say that U, let's not write it here, let's continue over here. So you can say that U is indeed greater than U prime. So the energy actually decreases. Okay, so it's a long-winded steps. I put a lot of time, probably about half an hour to think about how this question should be done. And yeah, but from here we can cross out a few options. The total energy indeed decreases, but energy is not conserved. So yeah, we still confirm that our answer will be D. But I think the steps here, it's quite difficult for level. It took me some time to figure it out as well. But I hope you see the idea and yeah, how I do it. How I end up using this equation instead of half CV square or Q square over 2C, right? It's a trial and error process. I've tried all the equations available, and I feel like this one is the easiest one to see the relationship. So I choose to express my explanation in terms of this equation here. That's it for question 4. Let's move on to the next question. Question 5. Two capacitors of capacitance C1 and C2 are charged to a potential difference of V1 and V2, respectively. If the two positive plates are connected and the two negative plates of the capacitors are connected, the systems of capacitors, so you have a capacitor which is capacitor 1 and capacitor 2, those are two capacitors, and both of them are charged to a potential difference of V1 and V2 respectively. So you connect the two positive plates here with a wire, then you connect the two negative plates with another wire. So probably something like what I draw right now. I still haven't connected the circuit yet because my drawing is before the connection. Okay, so now they ask what will happen to the system of capacitors, and the answer are asking you to analyze it in terms of energy and charge. Okay, so I believe it's quite similar to the previous question 4. We know that Q1 and Q2 should be equal to Q1 prime and Q2 prime, because if you have charges moved from the capacitor 1 to capacitor 2, the amount of charges lost in capacitor 1 will be the amount of charges gained at capacitor 2. Of course, it works the other way around as well. If here you lose 2 coulomb of charges, here you gain 2 coulomb of charges. This is just conservation of charges. You cannot create or destroy charges out of nowhere. Okay, So in that case, we can say that the total charge should remain constant. Okay, so let's look at this one. This one, loose charges, wrong. Loose charges, wrong. Loose charges, wrong. Oops. Charge remain constant, correct. Okay, so I believe the answer will be this one. Okay, so of course we can also analyze things in terms of energy, but forgive me for this one. I've tried quite a long time, probably for an hour or even more, to try and determine a way to really prove that the energy is indeed losing energy, but I still haven't really figured out a way to really explain the situation here. But what I can do is I can share with you what I have done until now. Okay, so we know that the old case will be C. Let's just write the energy straight away. Okay, since if you have better idea how to solve this problem, of course, feel free to just inform me about it. Okay, the old energy will be half Q1 V1 plus half Q2 V2. Okay, then the new energy will be half Q1 prime V1 prime plus half Q2 prime V2 prime. Okay, we know that V1 prime and V2 prime will be the same potential difference. The potential difference across here will be the same as the potential difference across here once you have connected the circuit. Because they are now connected by the same wires, there should not be any potential difference across the positive plates of C1 and C2. There also should not be any potential difference across the negative plates of capacitor 1 and capacitor 2. In that case, capacitor 1 and capacitor 2 should share the same potential difference. Let's just call this V prime. So we will have half, then you have V prime, then you have Q1 prime plus Q2 prime. Of course, you know that Q1 prime plus Q2 prime is equal to Q1 plus Q2. But I will not substitute it here because I still cannot see any reason to do so. Okay, so I am slightly stuck over here. There's also another thing which I tried, which I also stuck, which is using half C1 V1 square plus half C2 V2 square. So this is the old situation. Then the new situation here will be half C1 prime V1 prime square plus half C2 prime V2 prime square. We know that C1 prime and C2 prime will not be different from C1 and C2 because we are not changing the epsilon, we are not changing the A, we are not changing the D. So the capacitance should not change. So what this is what we know. C1 prime is equal to C1, C2 prime is equal to C2. We also know that V1 prime is equal to V2 prime. So actually we can also factorize it out to become V prime square C1 plus C2. Of course, once I reach here, I'm also quite stuck, not sure how to go forward with this question. I've tried to substitute V prime here with something. So like what we have done just in the previous question, what I do is I say Q1 plus Q2 is equals to Q1 prime plus Q2 prime. Okay, so we say that Q1 is equal to C1 V1 plus Q2 is C2 V2. Let's just write it as C1 V1 prime plus C2 V2 prime. You know that V1 prime and V2 prime are just V prime, so this one will be C1 plus C2. Okay, and this one will be C1 V1 plus C2 V2. So essentially you can say V prime is equal to C1 V1 plus C2 V2 over C1 plus C2. And actually what I did just now is I actually did arbitrarily try to substitute this thing inside. Okay, C2V2 over C1 plus C2. Then this will be V squared, then here will be C1 plus C2. Okay, and you will end up probably with something like this. Okay, C1 V1 plus C2 V2 square over C1 plus C2. Okay, you end up at this stage over here, which actually you can combine them back to be Q1 plus Q2 square divided by C1 plus C2. But if you try to compare it with the initial, which is U equals to Q1 square over 2C1 plus Q2 square over 2C2, I still can't see how to really effectively compare them and say that U prime is greater than U or U is greater than U prime. So I'm a bit stuck there. But if any of you manage to find out the answer, yeah, feel free to tell me. I'll probably be really happy if someone find out the solution for me, as I'm really frustrated that I haven't found the answer for a few hours. Okay, so but we know that the answer is definitely this answer because we know that the charge must remain constant. Okay, so that's all for question 5. Let's move on to the next question. Question 6. The figure shows two ways of connecting two identical capacitors of capacitance C to voltage supply V. Okay, so there's two figures here, figure 1 and figure 2. I've drawn it out. For figure 1, you're connecting two capacitors in series to a power supply. Let's call it V. For second situation, you're connecting two capacitors in parallel to the voltage supply, which is also V. And now they ask for the total energy stored in circuit 1 divided by the total energy stored in circuit 2. So how should we find this thing is, what we can do is we can change it to the equivalent capacitance first. So it means by we convert it into one single capacitor. In that way, it will be easier for us to determine the energy stored in that equivalent capacitor. Okay, so we'll convert it to something like this, and we will convert it to something like this. Okay, so of course, if we have converted to the equivalent capacitance, what happens is the V across the power supply will also be the V across this equivalent capacitance. Okay, so the same thing over here, the V for the voltage supply will be also the same as the V across this equivalent capacitor. Okay, so what I can do now is determine the energy initial, and not energy initial, energy in circuit 1, U1, and we can call it as half C. I'll write equivalent here just to make things clear. You can just write C, that's fine as well. But how do we find equivalent capacitance for two capacitors connected in series? What can we do is 1 over C1 plus 1 over C2 and over V squared. So we know that C1 and C2, they are identical based on these two identical capacitors, this statement here. Okay, so probably we can revise our equation a bit, be 1 over C plus 1 over C. Okay, so for now, you can do a bit of manipulation, then you'll find that this is just equal to C over 2 V squared. So now you arrive at 1 over 4 CV squared. For figure 2, it will be also half C equivalent. Let's just write a parallel P over here. And that's why I'll write an S for series. Okay, just to keep things clear. Okay, so for two capacitors connected in parallel, it's just C1 plus C2. Oops, I can write C1 and C2, it's just C. Okay, C plus C, V squared. So you arrive at CV squared minus 2C V squared. Therefore, CV squared. Okay, now they ask for circuit 1 over circuit 2. So it's U1 over U2. So it's 1 over 4 CV squared divided by CV squared. So the answer will be 1 over 4. The answer is the first choice over here. Okay, so there's more energy stored for the case where you're connected in series. There's less energy stored if you connect them in parallel. There's less energy stored if you connect it in series. There's more energy stored if you connect it in parallel. Okay, parallel more energy. Okay, so that's it for question 6. Question 7. The charge in the capacitor increased from Q1 to Q2. In which of the following graph of potential difference against charge Q does the shaded area represents the increase in energy stored in the capacitor? Okay, they ask for the increase in energy stored should be represented by which shaded area. But if you refer to my lecture notes on chapter 2, you learn that the derivation involves understanding a graph which is a QV graph. In this case, it's a BQ graph. Okay, you can deduce from the equation that half QV is actually just an area of a triangle. Okay, area of a right angle triangle in this case. So the height in this case should be V, whereas the width in this case should be the Q. Okay, so you have something like this. Then you have V times Q times half, then you get your energy. So based on this statement here, you will know that if the graph of V against Q is like this, then the shaded region below here will be the energy stored. Okay, but if you look over here, it seems that this is not very probable because they are asking for the increase in energy. They are not asking for the energy stored. They are asking for the increase in energy. Means by we are not asking for the whole area. Initially, this capacitor has some amount of energy. Then finally, it has an energy which is even more than the initial. So there's an increase in energy. It doesn't start from 0. It was not from uncharged to charged. It was from a certain amount of charge to another amount of charge. If you see here, it's Q1 to Q2, right? It's from an amount of charge to another amount of charge. So probably not the whole area here. But they also mentioned quite clearly that it's from Q1 to Q2. So I believe if you are able to determine where is Q1, if you are able to determine where is Q2, then it will just be the shaded region below below this line from the region of from the domain of Q1 to Q2. I believe what I've shaded in green here will be the answer. If you look over here, our answer here will be B. That's it for question 7. Question 8. An uncharged capacitor C is connected to the circuit shown in the figure. Which of the graph represents the variation of the current in the circuit with time after the switch is closed? Okay, so this is a previously uncharged capacitor. Then you connect it to a circuit with a battery. Okay, you are connecting it to a charging circuit basically. So when you close the switch, then the time starts. So what does it mean is when you close the switch, the charging process starts and the time starts at the same time. What they ask for is the change of the current with time. Well, this one I've explained it in class. For any charging or discharging circuit, the amount of current that is flowing will be decreasing with time. Okay, no matter it's charging or discharging, the graph should always look something like this. Okay, if it's a charging process, the I approaches 0 because more and more charges are now being stored at the plate already. So you have less and less charges actually moving in the circuit itself. You can think of it that way. Okay, but the proper way of thinking about it is if you are storing charge at the plate, let's say you have stored a significant amount of positive and negative charge in the plate, what will happen is if you are still connecting it to a battery and a resistor, let's say, then any charge which is attempting to move towards the positive plate will be greatly repelled by the positive charge that is already in the plate. So if it gets harder and harder to move a charge over to the positive plate, so if it gets harder and harder, less and less amount of charge will be moving in the circuit. So when there's less and less amount of charge moving in the circuit, reasonably you can say that the current is actually decreasing. Okay, that's the process for charging circuit. The current should be decreasing. If it's a discharging circuit, let's change a bit the circuit. If it's a discharging circuit, then probably let's change it to a resistor only. Then what will happen is the charge that was previously stored in the capacitor will come out from the positive plate and move towards the negative plate. Of course, there's only a finite amount of charge. There's only a fixed amount of charge that was previously in the plate. So of course, if most of the charge has already left the positive plate, then there will be less and less charge moving, right? Okay, so at some point in time, you will be left with less and less charges over here. So if there's less and less charges, of course, there will be less and less charges moving in the circuit from the positive plate to the negative plate, right? So in that case, of course, the current will be reducing. Okay, so in both the charging and discharging cases, the current should be decreasing with time. So the answer for this question should be the last selection here, D. That's all for question 8. Question 9. When a capacitor discharges through a resistor, the time constant of the circuit is the time after there's a lot of 1 over E and 1 over 2 initial charges, flow out, remains, all this kind of stuff. So what can we say? Now we see in the question here, it says that the capacitor is discharging. Okay, then it asks for time constant. So discharging is a process where you have a lot of charge stored in the plate first. You have charges on your plate. Okay. Then what happens is you connect the two plates here through some kind of load, let's say a resistor. Okay, then what will happen is charge will be leaving, positive charge will be leaving the positive plate and approach the negative plate, sort of trying to neutralize the situation. So the charge stored will be decreasing. Okay, so how should we express this situation? Here is there's a formula. Q is equal to Q naught E minus T over RC. So this is the equation we use if capacitor is discharging. Okay, so then they ask for the time constant. What does the time constant mean is we know time constant is equals to RC. Okay, so what happens when time is equal to tau? What happens when time is equal to tau? When time has hit time constant, what will happen is Q will be equal to Q naught E negative tau over RC. We know tau is equal to RC, so we can change the equation to become negative RC over RC. Okay, then we may move further to call it E negative 1, then this should be Q naught 1 over E. So what does this tell us? Q naught over here represents the amount of charge that we have initially stored in the capacitor. But now this amount of charge left on the capacitor is the initial multiplied by 1 over E. So now when time is equals to RC, right? When time is equals to RC, or when time is equal to time constant, what happens is you have less charge in the capacitor plates, but amount of charge left at the capacitor plate will be 1 over E of the initial charge stored at the plate. Okay, so with that said, we can say that the answer will be this one, 1 over E of the initial charge remains in the capacitor. There's initial amount of charge Q0, but when time reach time equals to RC, then you're left with 1 over E times the initial amount of charge you have at the start. Okay, A is wrong because initial charge is stored, not flows out. Flows out wrong. 1 over 2 definitely wrong. So our answer will be 1 over E of the initial charge remains in the capacitor. So that's all for question 9. Question 10. In circuit 1, a charged capacitor, which is this one, is discharged when the switch is closed. In circuit 2, the uncharged capacitor, this capacitor here is uncharged, is charged when the switch is closed. So we can know that C1 here, circuit 1 here, it's a discharging circuit, whereas C2 over here, it's a charging circuit because we have a battery over here. Okay, when the switches are closed, one of the 4 meters gives the reading data which varies with title as shown as shown below. Okay, so there are 4 meters over here. Then when time starts, all of them will record different kind of reading. So they're asking for which type of meter here records such a reading, which is shown in the figure. So as you can see, the reading here should be increasing with time. And we need to find what meter here actually increased with time. Okay, so let's try and analyze it one by one. Let's try and analyze this V1 over here. Okay, V1 over here, and it's connected across a charged capacitor. You see here in circuit 1, they mentioned that this is a charged capacitor. So if it's a charged capacitor, it must already have some kind of potential difference across them. Because it's charged already, there's charge over there, then there should be potential difference across them. So you know that this graph here definitely starts at the top. Okay, somewhere which we can call it as V0 probably. Okay, so when you close the circuit here, what happened is the discharging process started. So charge will start to move away from one plate and move towards the another plate. Okay, so you are losing charges when you are discharging, you are losing charges. So according to C equals to Q over V, C is constant away because you are not changing the capacitor in any way. If you are losing charges, then reasonably your potential difference should decrease as well. Okay, because you are losing charges, you cannot hold so much potential difference between them anymore. Okay, so what will happen is it will definitely decrease. Okay, so it's a decreasing graph, but as you can see here, the answer asks for an increasing graph. So V1 here will not be our answer. So let's move on. V2 over here. V2 is measuring across, V2 here is measuring across the resistor. Okay, so when we are talking about resistor here, the resistor here doesn't really affect the circuit in a very significant way. For resistor is very straightforward. It's always V equals to IR for resistor. Okay, if you have a great amount of current, then you have a great amount of potential difference. If you have less current, then you have less potential difference. The R here is fixed because this is a fixed resistor. Of course, the resistance is fixed. So now the amount of potential difference across the resistor is actually depending on the current flowing through the capacitor. But we have discussed in previous question 9, that for any kind of circuit, be it charging or discharging circuit, for charging or discharging circuit, the current against time graph should always be decreasing. It should always be decreasing. So since we say that R is constant and V is equal to IR, we know that V2 here should also be decreasing with time. Okay, they should be directly proportional, right? V and I. So if I is decreasing, V should be decreasing as well because R is constant. So again, V2 is a decreasing graph. We're asking for an increasing graph, so of course V2 is not the answer. So how about the ammeter graph? Ammeter graph over here. This ammeter here is measuring current. Well, I think it starts to get a bit boring now. If it's measuring current, as I've just said about half a minute ago, current should always be decreasing, be it a charging or discharging circuit. I'm not drawing it the best way that I can. If you're drawing this kind of circuit, right, it should start on the y-axis, but it should approach an asymptote at the x-axis. Okay, so the current is decreasing as you are charging the circuit because slowly it gets harder and harder to charge it, so slowly less and less charges will be flowing. Okay, so I think we are left with 1 meter, which is V3. Okay, V3 here is connected across the capacitor, which is now being charged. Okay, as you are charging capacitor, you are actually accumulating charges at the capacitor. You are accumulating charges at the capacitor. So as you are accumulating charges across the capacitor, what will happen is charges increases, therefore potential difference should actually increases. So with that, we know that the graph should look something like this, where it is approaching some kind of asymptote as well. We actually learned about the equation for this fourth graph over here, which is a charging circuit. So the formula should actually be V equals to V naught 1 minus E over T minus divided by RC. Okay, so this is for a charging circuit, the potential difference across the capacitor for a charging circuit. Okay, so the answer for question 10 should be V3 then. Okay, it's V3, which is showing this shape over here. Okay, so that's all for question 10.